All right, welcome to part two. So an object doesn't have to be moving or rotating to have angular momentum. That's weird. But here's an example. We're going to make some sense of it. Say you are standing here. Okay, so this is our reference plane. And then overhead, there's a plane. Okay, that's following this trajectory in a straight line over you. So since this is my reference plane, the airplane, that's confusing, the airplane is moving in a straight line, not in the reference plane. So in this case, it does have angular momentum. And let's see how fancy I can get. Oh, hang on. I'm trying to show you a picture. Well, I don't know how to do that. All right, I was going to show you a picture on a separate screen, but no biggie. Okay, so we have this moving outside of the reference plane, and our radius of this object moving outside of your reference plane is going to be the distance of closest approach. Okay, so wherever it is closest to you, which is going to be straight overhead, that's the radius. That's the value you use to calculate the angular momentum. Now, it doesn't matter where the airplane is in its path. It doesn't have to be straight overhead. The radius is the same for the entire path, whether it's here or overhead or over here or all the way over here. As long as it's moving in a straight line, okay, the radius is always the distance of closest approach. Okay, so we're going to see some examples of this where we have an object moving in a straight line, and other times, so if we have a lot of times the reference will be like a point of rotation. Okay, so the example we're going to see later, we have a stick, and some object comes and hits it and makes it rotate. Okay, so this is going to rotate about the center of axis, so center of mass. So that would be our reference, and the radius would be the distance closest approach. It would be from our center of mass to this point where it hits the object. Okay, that's just to give you context. We'll do that problem in a little bit. All right, so just like with linear momentum, we didn't spend much time figuring out what it was. Most of it was conservation of momentum. And that's really most of the problems that you're going to see with angular momentum is conservation of angular momentum. And also, just like with linear momentum, this is going to be in a closed system. So our net torque is 0. Those are going to be the systems we'll be dealing with, so we can actually apply conservation of momentum. Now, the best example of this, well, one of them, you've heard this term before when we were talking about Kepler's second law. Now, circular motion seems like forever ago, but we had those 3 Kepler's laws. The first one was with the orbits are ellipses, and hooray. Second one, that was the one that said whenever you have an object in orbit, so say that's the sun, say this is the Earth's path, the Earth orbiting the sun, or any object orbiting anything else, is moving fastest at what point? Think about it. You remember? Feel like Dora the Explorer. That's right, kids. It's moving fastest when it's closest to the sun. Okay, so that's where it's fastest. But we can explain why, using angular momentum. Okay, so if we look at this system, so we have a Sun-Earth system, and it is a closed system. You're like, but there's all the gravity. But remember, yes, the sun has a gravitational pull on the Earth, but Newton tells us, with his third law, that the Earth pulls equally back on the sun. So when you look at this as a system, the net torque is zero. Just like when you have a collision and two cars hit each other, car one hits car two, but car two hits car one with the same equal and opposite force. So that's what we could call those collisions closed systems. Even though there are forces happening, as a system, it is closed. Okay, now back to angular momentum. The mass of the Earth is the same whether it's there or whether it's here. That's going to be the same. The radius here is at its smallest. Radius here is at its biggest. Velocity here, that is its highest, and that is its lowest. And if you look at our equation for angular momentum, mvr, if our angular momentum is conserved, that means it's the same at either place. And that is possible because as our radius decreases, our velocity increases, and vice versa. So when you do the math, it all balances out, and our angular momentum stays the same. So that's really the concept that backs up Kepler-2. It also makes sense when we do that law of equal areas, but that's a really common application of conservation of angular momentum. The other, more fun one, is when you just think of a spinning skater. Okay, if you've ever watched figure skating, you all have, even if you won't admit it, when they go to do those like really fast spins, what do they do with their arms? Well, they pull them in close to themselves. I'm going to let you experience this by spinning in a chair. So you can tell the sub, I'm letting you do this, but I want you to do this. So someone adventurous in class, get up and drag a friend up there, take the wheelie chair and put it like in an open area, and someone go get like 2 of the 2-kilogram masses that are in the back under the sink. Go do it. And then what I want you to do is have someone sitting in the chair and holding one of the masses in each hand, and then someone get them spinning. Okay, they can be holding them wherever. And then while you're spinning, I want you to bring the masses in close to you, and then hold them straight out from you. So you're going to extend your arms out, and then bring them back in, and see what happens to your rotational velocity. Okay, do it a couple times, see it, then everyone else is going to want to do it, and that's okay. You guys can spin for a while. So pause the video and go do that. Ready, go. Okay, wasn't that super fun? Oh my gosh, good job. Okay, so you did the spinning chair. Now, let's see what happened. So you need to think about what variable changes when you bring your arms in. Okay, so if we think about all the variables involved with angular momentum, whether it's I omega or mass velocity radius, the mass of you and the masses you're holding is not changing. Okay, but when you bring your arms in, you decrease the radius. Now, if you think of this in terms of rotation and a moment of inertia, we talked about this with the different shapes. If you have more of the mass closer to the center or with a small radius, you're going to have a smaller I. Okay? When you bring it out, you have a bigger moment of inertia because all that mass is distributed outwards. All right, next video.